We are live, 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 we are live. Alright, so it's time to start. It's time to start the stream.
Take a moment right here, feeling like it's out gear. Driving towards the sun with a rose and a gun. Feel the wind in my hair, going nowhere I swear. Like an outlaw on the run, dangerous but it's so fun. Running, running, no. Hold on, don't let go. Running, running, no. Keep running. Running low, keep running. I'm running low, keep running. Like an outlaw on the run. Dangerous but it's so fun. Oh, running low, keep running.
What's up with y'all boys, man? What's up with y'all boys, man? What's up with y'all, bro? Welcome to the stream. So today, first I'm gonna teach you guys some stuff, and then we're gonna jump into some code forces solving. Alright, so let's start now. So first we got count. We're gonna find out how to count digits in base. We're gonna find out how to count the digits in base. So I already told you guys how to convert from decimal to a base yesterday. So basically in this problem we are given an integer in decimal and we want to count the digits of that integer in base B. So what do? We make a digits array where we keep the digits, and then we insert each digit. Basically this is gonna convert the number from decimal to base B. So we're going to this is gonna get, and to get, as I explained yesterday, to convert a number from base 10 to base B, we divide that number by the base number. So in this case it's gonna get divided by 8, and we keep track of the remainder. So right now the decimal number is 8, and we're gonna convert it to base 8. So when we divide 8 by 8, the remainder is 0. So that remainder will get pushed into the array. And now the array will look like this. It's gonna look like this, 0. And we're gonna remove the last digit from that. Okay, and then we're going to divide this number by the base. So 8 divided by 8 is equal to 1. Then finally we're going to push this base, the number divided, the remainder of n divided by base. So n is 1 right now. When we divide it by 8, the remainder is 1. And that is how we're going to count the digits in the representation of the number from decimal into this base. Okay, so let's just run this file and show you guys that it works. So this is count digits in base of O, and this is count.exe, and we're gonna do count.exe, and this is gonna give us 2 because there are 2 digits in the octal representation of 8. Since the numbers are 0, 1, 2, 3, so octal, the numbers are 0, 1, 2, 3, 4, 5, 6, 7. There are 8 numbers. We cannot write 8. Afterwards comes 10, 11, 12, and so on. So this is in octal. So now let's try an example in binary. So we're gonna put 7, and we're gonna count in binary representation the number of digits in the binary representation of 7. So that is going to give us 3. That is going to give us 3. All right. That is going to give us 3, and there we go. We get 3. Okay, and that's pretty much it for this one. Okay, the next one is which one should it be? Okay, the next one is Pascal's triangle. So the problem statement is get the sum of the nth row in Pascal's triangle. So the statement, so actually question, get the sum of the nth row in Pascal's triangle. Okay guys, so if you guys don't know what Pascal's triangle is, it's this. You've probably seen this in school in your math class. So this is the first row, 1. This is the second row, 1 and 1. This is the third row, 1 and 2. And basically there are 2 ways to get the nth row, the sum of the nth row. So basically to get it, the sum of the nth row in Pascal's triangle is 2 to the power of n. It's 2 to the power of n. So the sum of the first row is 1. The sum of the second row is 1, which is 2 to the power 0. The sum of the second row is 2, which is 2 to the power 1. The sum of the third row is 4, which is 2 to the power 2. The sum of the fourth row is 8, which is 2 to the power 3. So basically, we need to power 2 to the power of the number of the row minus 1, because as we can see here is the fourth row, but 2 to the power 4 is not 8. 2 to the power 3 is 8. So let's say we are on the 1, 2, 3, 4, 5, 6th row. This is the 6th row, so this is gonna be 2 to the power 5, which is 1, 6, 16, 26, 31, 32, which is 2 to the power 5. And how can we solve this? Well, we could just up that number to the power. So we can use a built-in power function, or we can do the powering or logic by ourselves. But this is going to take longer. This is going to be slower. A fast way to do this is left shifting 1 by n minus 1. So why does this work? When we left shift a number, we multiply it by 2 to I. In this case, I is this right here. So if we left shift 1 by 1, we are going to multiply it to 2 to the power of 1. So let's say we have 1 left shifted by 1. This is going to be equal to 2 to the power 1, which is equal to 2. And let's say we have 1 left shift 2. This is is going to be equal to 1 0 in binary. Then we have 1 left shift by 2, so this is 2 to the power 2. This is going to be equal to 4, 4, and this is equal to 1 0 0 in binary, okay, and so on. So this is why it works. When we left shift 1 by a number, we are basically multiplying 1 times 2 to the power of what the number which are shifting by. So here we're shifting by 1, we are multiplying 1 times 2 to the power 1. Okay, this is 1 times 2 to the power 1. This is 1 times 2 to the power 2. Alright, so that's how that works. So when we left shift a number, we multiply it by 2 to the power, we multiplied by 2 to the power I. I is the amount we left shift by. In our example, I is equal to n minus 1. So our answer is 1 times 2 to the power. Our answer basically is 1 times 2 to the power of n minus 1. This does the same as 1 left shift n minus 1. Because we already explained that this when we left shift 1 by our number, it is 1 times 2 to the power of whatever we shift to. Okay, and again, since the triangle is we count the rows in the triangle from 1, so 1 2 3 4 5 6. When we want the sum of the first row, is going to be 2 to the power of 8 of 0, which is n minus 1. So this is, if n is 1, it's going to be 2 to the power of n minus 1, which is 2 to the power of 0. If n is 2, the sum is going to be 2 to the power of 1, which is 2 to the power of n minus 1, which is 2 to the power of 1, because n is 2. If n is 3, the answer is 2 to the power of 2, because again, we do 2 to the power of n minus 1, and n in this case is 3, and so on. Okay, so that's pretty much it for that one. Okay, so let's run it. Let's run this what is on Pascal's triangle sum dash O, and this is Pascal.exe. So let's compile run this. Compile run, and then we're gonna run Pascal Pascal.exe. Okay, what's it's got triangle sum. Pascal.exe. Am I doing something wrong? Pascal.exe was not recognized. I need to do slash pass. Okay, slash.pascal.exe. Okay, what is happening? Just close Pascal's triangle sum.cpp. Oh, it's a dot slash Pascal. There we go. It's dot slash, not slash dot. Okay. Okay, and then we should get something. Okay, there we go. So the sum of the first row is 1. The sum of the second row is 2, and the sum of the third row is 4. Let's get the sum of the sixth row, and this is gonna be 32. So we're gonna get 1, 2, and 32. 1, 2, and 32. 1, 2, and 32. There we go. 1, 2, and 32. And that's basically it for that one. Let's close these. Okay, that's it for that one. So this one we're gonna go after now. The next one is, how do we check if a number is a power of 2? So in its binary representation, a number, so in its binary representation, basically if a number is a power of 2, its binary representation is going to contain only a single set bit, or only one bit, which is 1. Let me repeat. If a number is a power of 2, that number in its binary representation will contain only one set bit, or only one bit, which is 1. As we can see, this is 1, which is 2 to the power 0. This is 2, which is 2 to the power 1. This is 4, which is 2 to the power 2. This is 8, which is 2 to the power 3. 0, 1, 2. And this is, okay, this is 4 again for some reason. Okay. Alright, so this is the rule. And now that we know, that if the number has only one set bit, then that number is a power of 2. So what are we gonna do? How are we gonna figure out if that number is a power of 2 if we know that numbers which are power of 2 have only one set bit, where we can count the number of set bits in the binary representation? So the first approach is, so first we do have an edge case where if the number is 0, in that case we just return false. Alright, in that case we just return false. Okay, otherwise we're gonna continue, so we're gonna keep a counter. So if we have found a set bit, we're gonna increment the counter, then we're gonna right shift. And if counter is greater than 1, if there is more than one set bit inside this binary representation, that means it is not a power of 2, so we return false. And if we have gone through the entire number without encountering more than one set bit, that means that it is a power of 2, and we return true. But this is actually not the most optimal solution, because this is O of n, O of number of set bits. So depending on how many set bits depending on how many bits the number is in its binary representation, this while loop is gonna run that much times. So the optimal solution is actually the following. If we're gonna have our edge case, if n is 0, just return false. Else we are going to check if the number ending it with the number 1 less than it is equal to 0. So for example, we have 1, 0, 0, which is 8, which is power of 2. Then 8 minus 1 is 7, which is 0, 1, 1, 1, which is 7, and this is equal to power to, this is n minus 1. And when we AND all of these, 0 and 1 is 0, 0 and 1 is 0, 0 and 1 is 0, 1 and 0 is 0. And now that this number, and now 8 and we can see that 8 and 7 is equal to 0. And I'm pretty sure this is called like a 2's complement or something like that. This is called like a 2's complement or something like that. So we can check it for another number that is a power of 2. Let's say we have 16. 16 is 1, 0, 0, 0, 0. This is 16, which is a power of 2. So we're gonna end it with 16 minus 1, which is 15. So there is 0, 1, 1, 1, 1. This is 15, and this is going to give us 0 because 0 and 1 is 0. 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 1 and 0 is 0. So 16 and 15 is equal to 0. Hope you guys are getting the grasp of it. So, but let's say we have a number which is not a power of 2. Let's say it's 15. But let's say it's 1, 1, 1, 1, which is 15, which is not a power of 2. If we say 15 and 15 minus 1, we're going to get 1, 1, 1, 0, which is 14. And so when we say 1 and 0 is 0, but then 1 and 1 is 1. 1 and 1 is 1. 1 and 1 is 1. And basically, 15 and 14 should give us 14. So that is not equal to 0. And then this will not return true. Okay? So we have some tests here. So we're gonna try, we have both the naive one and then we have the optimal one. So we're gonna try 16 here and we should get that. Okay, this is, what is happening? I don't understand. I mean, well, welcome to the stream, Slinky. I'm just trying to teach you guys some stuff. If you want, you can rewind the stream. I mean, I already went through it. If you want, you can rewind the stream and watch it again, or you can watch it again when the stream is over. It's your choice. Or if you don't want to watch it again, that's fine too. Okay, so now we should see that. So this is, I basically just went over how to figure out if a number is a power of 2 using bitwise logic. Using bitwise logic, how to figure out if a number is a power of 2. That's what I just went over. So let's run this power of 3 of 2. That's short, that is, it's called is power, let's call it power 2.exe, and then we're gonna run power 2.exe. Okay, gonna run this. Okay, so we get 15 is not a power of 2 and 16 is a power of 2. Okay, and that is correct. Now let's say this one is going to be the power of 2, which is going to be 64, and then this one is going to be not the power of 2, which is going to be 12. So we should get 64 is a power of 2, and then we should get 12 is not a power of 2. Okay, that's what we should get. Okay, 64 is a power of 2, 12 is not a power of 2, alright? And that's it for that one. Okay, so is that okay? So that was it for that one. Then we have the last one, which I think is the most interesting one. In my opinion, I mean these ones are also interesting, but I think this one kind of takes the cake. So the question is, raise the number to the power of p, to the power p, to the power of something. And we actually have two versions right here. So this version doesn't work. and it actually took me like a while to wrap my head around why this doesn't work. And then we have a version which it does work. I'm gonna explain both of them. We're gonna see why this one doesn't work and why this one does work. Okay? I mean, the approach is the same, it's just the logic that makes them do. So what is the idea? The idea is we're going to have a number. So find number. So the question is question find number raised to power p or something. Okay, now what can we do? We can let's say our number is 3 and the power is 6. So what can we do? We can start multiplying 3 times 3 times 3 times 3 times 3. But this is not an optimal solution because in this case, the time complexity when we start 3 times 3 times 3 times 3 times 3, that's 5 times 3. The time complexity is going to be O of P, where P is the power which we're gonna raise by. Okay. A more optimal way to do this is we can use bitwise logic again. And we can. So basically, we're going to use the binary representation of P, which is 110 in which is 6 in binary. We are going to have our base set to 3. Then we are going to, so for each one of each time this is 1, we're gonna multiply. So we're gonna have our answer which is equal to 1. Then we are going to have this in binary, as we can see here. Okay, then we have our base. All right, and now we're gonna run a loop while p is greater than 0. We're going to right shift by 1, and we're going to multiply base by itself, and then we're going to multiply the answer by base. So basically, when p is equal to 110, the base is going to be equal to 3, answer is going to be equal to 1. But this time we're not going to multiply because this one, we're going to do n1, and this is going to be 0. Okay, but when p, then we're going to right shift p by 1, like this, and now p is going to become, now p is equal to 1 1, and now 1 1 and 1, this is equal to 1. So we're going to say ans equals ans times base, which is 1 times 9, because on each iteration we're going to say base times equal base, and here base is equal to 3 times 3, which is equal to 9, and then yeah. Okay, and we're gonna do this on each iteration. So this is the answer right now. Now base is going to be 9 times 9, which is 81. Since the last base is 9, we multiply base by itself. We can also write base times equals base, or base equals base times base. Now we're going to right shift p again. Now p becomes 1, and 1 is equal to, no, not times, and 1 is equal to 1. Okay, so that means we're going to multiply ans times equal base. So right now this is going to be ans is going to be equal to 9 times 81, which is 729. Then we're going to right shift p by 1 again, then P is going to be equal to 0, and then we're going to break, and we return the answer. Okay, what is wrong? It's better declaration. Okay, I don't know. Okay, so we have a wrong version. So this version is wrong because what happens here? So what happens here? Right here, what happens is, okay, this is the other one. So this is this one. So initially, base is going to be equal to n equal to 3. Then p is equal to 110. Then the last bit is 0, so we're not gonna increment. Then we're gonna say p is richer by 1, and then we're gonna say base equals base times n, or this is 3 times 3, which is 9. Okay, so far so good. Then on the next iteration, p is equal to 1 1, which and 1 is 1. So this time we're going to multiply ans with base. As we can see, we multiply ans with base when this gives us a trophy value. So ans times equal base, which is ans equal ans times base, which is ans equal 1 times 9, which is 9. Then the base will become base equal 9 equal base times n. Now, why is this a problem? Well, it's right here because this is going to be equal to base equals 3, actually 9 times 3, which is equal to 27. Okay, and as we can see, when we dry run this, right now base should be 9 times. So on the second iteration, base should be 9 times 9, which is 81. But here on the second iteration, base is equal to 9 times 23. Base is equal to 27, which is 9 times 3. And this is bad because now we're going to p to 1. Then p is equal to 1 and 1, which is equal to 1. So we're going to say ans times equals base. So ans right now is 9. Yes, ans is not ans is equal to 9 times 27, which gives us 243. Here it should have been 9 times 81, but it is 9 times 27, and this is why we cannot say n here. What we must say is that we can't multiply by n, we multiply by base. Okay, so I already explained the correct approach, so this is right here. So this I wanted to point your guys' attention to this because it took me like 30 minutes to figure out why, or maybe not, maybe like 10, but it took me some time to figure out why when we multiply by n the base, it does not give the correct answer, and this is why. Okay, so as we see here, there's another dry run. So this is 3 raised to the power 6, and it's gonna give a correct answer, which is 729. Now let us run this file. So raise to power dash o raise.exe, and we're going to see that the first answer is going to be 243, which is wrong, and the second answer is going to be 729, which is correct. Wait, no, this is to 3. We need to do to 6. We need to do to 6. And guys, it is very useful to learn this trick because this takes your it takes your solution from O of n to O of log n. So that is so much faster. That is so much faster. Raise.exe. Okay, and we can even check what is this. Right now I am explaining some So basically, I'm explaining some approaches right now. Uh, yeah, I started explaining immediately. So if you want, you can watch the stream later. You can rewind the stream, or you can watch it after it's done, and then you should be able to be a little. You should be able to, understand what's going on. Then basically, I'm teaching you guys right now how to raise how to raise a number to some sort of power without using the pow function and with an optimal approach. Okay, I needed to do. Okay, wait a sec. What did I do? Okay, this. Okay, raise to power, raise. Okay. Um, we are gonna. Okay, let's see if this works. Okay, there we go. We get our wrong. So the raised to power wrong gives us 243, and the raised to power correctly gives us 729. So that is what we want, and we can check this. We can check this. Okay, we went over the powers of 2 already. We can check that 3 to the power 6 is 729, and 3 to the power 5 is 243. So that's what's happening here. Okay, you guys, okay. I think that is basically all of the what I wanted to teach you guys. That is basically what I wanted to teach you guys. Again, guys, if you tuned in and related to the stream, I would suggest rewinding back, and you will. So I suggest rewinding back to the start of the stream, and then things will be more clear. Now I know I'm not the best at explaining, but I hope I hope I was kind of able to explain this. Okay, so now we're gonna go. Okay, yeah, and this is what I wanted to show you. So yeah, so basically, if we do it the regular way, the regular power, which is multiplying all the numbers. So let's say we want to raise 3 to the power of, let's say we want to raise 3 to the power of 3. We need to do 3 times 3 times 3. But if we do instead, uh, and this is going to be O, big O of power, which is the power. But if we do the optimal solution, optimal is big O of log of power or something like that. I'm pretty sure. So this is as we can see on this chart, we can see how much faster O of log n is in comparison to O of n. Okay. Okay, so that's that one. All right. I am beginner coding. I mean, it's okay, bro. You can still watch the stream. That's okay. Congratulations for starting, because a lot of people get scared and they don't start. So congratulations for starting. Okay, so now we're gonna solve some code forces, or at least we're gonna try. Okay, so I opened up this one. Okay, we can close this. I opened up this one. Give it an integer, and this is a bit masks question. It's rated only 800. Given an integer n, find the maximum value of k such that the following condition holds. Okay, let's zoom in a bit. So basically n minus 1 and n k, the maximum Okay, first I can taste t, so integer n, and find a maximum value of integer k. The first test gives the maximum value for which the continuous and operation gives zero value is 1 in the first test case. No problem, man, no problem. Where are you from, Niram? Where are you from? And how was your day today? Did you have a nice Sunday today? What did you do today? What did you do today? Okay, so the maximum value for which continuous and operation gives zero value is 1. In the second test case, the maximum value for which the continuous and operation gives zero value. Okay, so we want it to be equal to 0 is 3. Okay, no value greater than 3, say for example for regular sum. Okay. Mm, why did we start at 5? Okay, we're given 5, so we start at 5, 5, 4, 3, 17, 16, 15. Okay, okay, I think I got it, but we'll see. So int t, int t, t minus minus. So I think we can keep track of these in int n, cn, cnn, to give us answers. Okay, but when is the loop gonna terminate though? I love India. I love India. I love India. So when is the loop gonna terminate though? Has some value which contains an absorption gives. The case the following condition holds. And n minus 1 and n minus 2 and n minus 3 and k. Okay, I don't know if this is gonna pass. Equals 0. Hmm. So what happens if -1 in binary? What happens if there's negative numbers? Mm, decimal 2. Decimal 2. I am no ED. I have no idea what that means. Okay, so okay. Um, mm, 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 mm. Hmm. When do we stop? Single integer. The maximum give our zero is 1. If it's when 0 is gonna be it's a bitwise and on the line. I don't even know. Okay, let's just try it up until 0 and we'll see. Okay, for get n minus 1 I create equal to 0. J gets I j equal to 0. J minus minus. I'm gonna say int res n equal j if res equal to 0 answer that push j, and then we're gonna see out max element answer that begin answer that end. Okay, hello, learn with Adi Sharma. Welcome to the stream. What kind of coding is this? This is competitive. This is maybe competitive programming, but it's just DSA. It's data structures and algorithms, I would say. No, it's gonna be push back. Okay. So we're gonna see what's 3. Let's say 3, 2, 3, 2. Okay, we get 1, 5. Gets 4. What the? Equal. Okay, I'm gonna say close to I, and then I minus 1. Something like that. 2. So, okay, what? We're sec. Okay, we get 2, and then we get, what do we get? 0. Okay. Why do we get 0? So let's say this is 2. Okay, I think So it's 1, it's gonna be 1 and 0. No, it's gonna be, wait, so n is equal to 2, then this is gonna be, so I is equal to 1, then res is gonna be equal to 1, and then g is gonna be equal to 0, and that's why that happens greater than or equal to 0. So equals j. Okay, okay, let's change it up. Let's keep it as it was. Okay, I think it was 0, right? Okay, we get 1 here. And then we get, it's 5. Okay, it gives 4. Should give 3, and then 17, gives 16. Okay, let us, so we want it to be actually, this actually needs to be n, I think. Because it's and n minus 1 and n minus 2. Okay, do we even need a second loop? Bye. See ya, man. Goodbye. Thanks for stopping by, bro. See ya. Bye bye. Okay, so it's going to be equal to n and n minus 1. Okay, let's try this. So 3, 2. Okay, 1, 5. Okay, 3, 17. Okay, 15. Okay, let's see if that works or what. Okay, we need the 1527A. 1527A. Let's see if we there's a wrong case. We're gonna fix it. Okay. Time limit exceeded. On this too. Go to Python language. I mean, I've used Python as well. You can do this. You can solve these questions in any language. You can solve them in Python. You can solve them in JavaScript. You can solve them in whatever language you want. Okay, let's see what's wrong here. Time limit exceeded. Yeah, I knew it was gonna be a time limit exceeded. 3,000. But let's see if we're getting the answer right at least. Okay, how can I shorten the time then? Not here. What was it? 8 times n minus 1. Small value of k. Some formula. Hmm. Hello. Okay, let's try another one. Let's try another one. Mm, which one? Which one? Which one? Okay, let's add brute force. As brute force implementation. Okay, let's try this one. ABC string. Oh hell no. Okay, let's read this. Okay, guys, the stream is almost over. We've been streaming for almost 1 hour. So yeah, you're given a string A consisting of n characters. N is even for each I from 1 to n. And A of I is one of ABC. A bracket sequence is a string containing only okay, open and closing parentheses. A regular bracket sequence is a bracket sequence that can be transformed into a correct arithmetic expression by inserting 1 and plus between the original characters of the sequence. For example, bracket sequences and this are regular. The resulting expressions are 1 plus 1 and 1 plus 1 plus 1 and this and this are not. And this one are not. Want to find a string B that consists of n characters such that B is a regular black bracket sequence for some I and J, then B is replace all occurrences of A with the same type of bracket, then all occurrences of B type of bracket, and all occurrences of C same type of bracket. Your test determine the string B exists. The first line contains single integer. Okay, whatever. Print yes if there exists a string that B is a regular bracket sequence for some I and J. J less than I and B equals B of J. I was print no, you made You may print every letter any case you want, for example, yeah, whatever. Yes. The possible strings B is AABBAC. Okay, I didn't. Hmm. Hmm. Okay, guys. That's gonna be it for today's stream because I basically haven't gotten up from the computer in like 3 hours. The screen has been blasting me with blue lighting for about 3 hours, and I've gotta get up. I was preparing the explanations for about like an hour. So yeah, that's gonna be for today's stream. I hope you guys learned something. I hope you guys were able to learn something from the explanations that I did in the beginning. If you missed the explanations, you can rewind the stream and you can watch them again. Thank you so much for everybody who tuned in. Have a nice Sunday, and I will see you in tomorrow.